Okay, last time we were here talking about line spectrum and the different uses of this, and so just kind of to make sure we're on the same page here, just the specific elements are going to give out very specific information. So the information hydrogen gives off is different than the information helium is gonna give off in terms of the line spectrum. So if we look, you can see that the hydrogen has values here and here and here and here. But if you look and you think of a rainbow, well, the only very small pieces of the rainbow are showing. So that's that discontinuous. So this is all gone, this is all gone, this is all gone, this is all gone. So you only see tiny, tiny, tiny bits of it. And so if you look at down here below at helium, it has different markers. And so that's because it's a different element. So that's sort of the idea. If you have this line spectrum, then you can tell what element you might have. So you can look at light coming from stars and different planets and things like that, and that's how they can say, well, this star is made of these elements, things like that. So let's go back and look at this piece here. IB always focuses on a very specific area, and so they talk a lot about hydrogen, and hydrogen is going to exhibit all the same properties that other things do, but they talk about hydrogen. So what they're talking about here is they say that when hydrogen atom gives out energy, so the hydrogen atom gives out energy when an electron falls from a higher to a lower energy level. So we're going to be talking electron configurations here, and so stuff that you did last year, like 1s2, 2s2, 2p6, 3s2, etc. Well, the energy levels are these rows. And so what happens is that there are multiple energy levels. There's 1, 2, 3, 4, 5, 6, and 7. And so what happens is that the farther you get from the nucleus, the closer the energy levels are. And so you can see this distance is significantly smaller as we go out. So that one's big, and then that one's smaller, and that one's smaller, and every level you go out, it gets smaller. So what happens is they call that convergence. And the energy levels are converging on each other. So when you get to the very end, they basically collapse on each other. And so the most energy is associated from going from energy level 1 to energy level 2, because that's the biggest distance. And so we're going to talk about these things, but one idea that does show up is that at the higher energy levels, those energy levels converge and they basically collapse upon each other. And so that's sort of what this bit of information is talking about. And it's talking specifically about hydrogen, although all of the elements would do the same thing. Okay, so here we go. Talking some specifics, some things that could be showing up on a test, on an exam. And it says how the line spectrum is produced. So the way you get this is that you have to add energy to your atom, to your element, whatever you're trying to get to give off energy or light. So think about a firework. The fireworks are not giving off any light in their container. You buy them. They're not blowing up. You take them home. They're not blowing up. You have to add the energy. So, I mean, you have your mortar shell at home, and it's not blowing up in your garage. Thank goodness, or your parents would be unhappy. And so there's your mortar shell, and then we drop the mortars in, but we light the fuse, right? So the key thing is that we have to light the fuse, and so that's going to go in there, and that adds the energy, and then that's when you see the colors. Well, those are the that's part of the line spectrum, the things that are released when your mortar shell goes up in the air and it makes a big firework. So boom, boom, boom. So you get a blue firework. Well, you've got to add that energy. So if you go over here to the nodes, the first thing we have to do to get these things to work is we have to add energy. So energy is added to atoms or molecules, causing them to, what happens is it's going to cause them to, and the spacing is kind of tight here. I didn't realize that. I changed the notes a little bit this year, and so this is where we're going to have to write that in, is in this space. That's a little bit tight, so I might zoom this in a little bit. So energy is added to the atoms or molecules, and it causes them to move, or causes them to elevate or move up energy levels. So it's going to cause them to elevate or move up to higher energy levels. So think about maybe going from energy level 1 to energy level 2. So the way that IB writes energy levels down is it writes down energy levels as N. So N is going to equal an energy level. And an energy level is the same as a row on the periodic table. So it's a row on the periodic table. And so it's not something weird. It's literally just talking about a row. And so you could have something go from like N equals 1 to like N equals 3. So it elevated energy levels because it went up. So this is an elevation. I went from 1 to 3. Right? So what happens is that you add the energy, they go up in energy levels, but then what happens is that they then come back down. Okay, and so then they give off the energy you added with the Bunsen burner or with electricity or whatever, and then energy in the form of, and you got a couple blanks here, in the form of a photon. And a photon is just a particle of light. Energy in the form of a photon or light is emitted as these electrons come back down. So you push them up and they come back down. So you push them up, they come back down. So so what happens is we call those electrons that are moving around, we call those excited electrons. Means we'd added energy. So the excited electrons fall back down to their usual energy level, or what we call ground state. Okay, ground state. So a couple things to note is that a ground state is what we would consider normal. That's the normal place. Okay, so what does that process look like? That process looks like this. You have the electrons are going to go up, you add the energy, and then they fall back down. So they go up, and then they fall back down. So it's just this process of going up and down. And so that's the light that you see from a firework. That's the light that you see given off from like a fluorescent bulb when you're heating up the gas inside of there. And so now there are specific types of these emissions or light given off, and we do need to know those specific names. And those are going to be right over here. Oops, don't want to do that. In that little diagram. Now yours is black and white, but mine is color. So it's very easy. You have to just memorize 3 things, and it's the series and the color or the wavelength associated with that. All right. So we have things that go to energy level 1. That's the UV or the Lyman series. So if you start somewhere and you end up in N equals 1, then the energy given off is going to be UV energy, and we call that the Lyman series, right? Second option, end up in N2. So n equals 2 is the Balmer series, and you can see the colors, right? Red and green, etc. That's visible. It means we can see that. So when we end up in the energy level 2, so if we end up in n equals 2, then that's going to be visible light. So this is actually what you see when you see things giving off light, like a fluorescent light. This is what we actually see, is we see the visible spectrum, and the visible spectrum is that n equals 2. Okay, so if you look over here, Balmer series n equals 2, all these arrows are pointed down. So these arrows are pointed down because they are landing in 2. Right? They're not leaving 2, they're coming back down to 2, and when they do, they're going to give off this visible light, and this is the Balmer series. Okay, and then the last one that you need to know is the n equals 3, and that's the Paschen series, and that is going to be our infrared. So n equals 3 is going to be infrared. So can't see that one, right? So let's go over here to the notes. I'm going to change my zoom a little bit. So if we go over the notes, it says the Lyman series, okay, that's the first one we talked about, are generated when an excited electron falls to, and this is really important, you should put a star by this, it falls to n equals 1. You have to memorize that. Okay, you have to memorize that. And these are going to be in the ultraviolet range, the UV range. Not a very good looking V. There we go. And then the Balmer series, you got to memorize this as well. We're going to drop into the n equals 2. Right, so that's going to be something we want to memorize. If you land in 2, you want to memorize 1, UV, and 2, that's going to be the visible range. All right, and then the Paschen series, you got to know that one as well, and that's going to be the infrared, so the IR. Okay, so just depending on it really just depends on which one it lands in as to what it is. Okay, so let's take a look here pretty quick. Transitions, and this is something to memorize as well. All kinds of things to memorize, I guess. So right here, not a very good looking star. Jeez. There we go. Transitions to the ground state. So ground state is n equals 1, right? That's the ground state. So transitions to the ground state, meaning if you hit number 1, which is closest to the nucleus, they are going to release the most energy. That is a test question. Always comes up on the test. So the distance from n equals 1 to n equals 2 is the greatest, because that is that one that we looked at over here. If we go ahead and we zoom in, this is what I was talking about right here. I was talking about this idea that this space from 1 to 2 is the greatest. So that's the most energy. And so that 1 to 2 is the most energy, right? All right, I'm going to pause it here. We'll pick up with some examples on the next video.